Hello students, this is Professor Chalai, and in this video we're going to go over some calorimetry calculations. As always, you can follow along with our Chapter 5 workbook. Before we get started, I would like you to attempt questions 6, 7, 8, and 9 in our Chapter 5 workbook. At the end of each, you can unpause the video and look at my solutions for each of them. If you think you have a good handle on how to solve these problems, you can skip ahead to where I show just the answer and compare it to your own answers, and then rewind to see where you might have gone wrong if you did get it wrong. If you don't think you have a good handle on the questions, answering these types of questions, that's okay. I will go through each of them in detail. Let's get started with number 6. If you haven't done so already, pause the video and work it out now. Okay. In number 6, we have two substances. We have copper and we have water. In most cases, one of the substances we're going to work with is going to be water because in our coffee cup calorimeter, usually it's filled with water. And there's a few reasons for that, one being that water has a very high specific heat capacity. But we have these two materials placed into contact with each other, starting at different temperatures, but eventually coming to thermal equilibrium with a final temperature that's 24.2 degrees Celsius. So before you attempt problems like these, I would write all of the pieces of information for each of the two materials that were given. So let's start with copper, right? The mass of copper is unknown because that's what we need to find in the question. The initial temperature is 65.4 degrees Celsius. So the initial temperature of copper is 65.4 degrees Celsius. What else are we given? The copper, the final temperature is 24.2 degrees Celsius. That's going to be true for both the water and the copper because it's in thermal equilibrium. So the final temperature is going to be 24.2 degrees Celsius. And finally, here we have the specific heat capacity of copper, which is 0.385 joules per gram per degree Celsius. Okay, let's do the same for water. Let's write all the pieces of information that we have for water. The amount of water that we have, the mass is 95.7 grams. The initial temperature is 22.7 degrees Celsius. The final temperature is 24.2 degrees Celsius because it's at thermal equilibrium, so the final temperatures are the same. And the specific heat capacity of water is 4.18 joules per gram per degree Celsius. Okay, now that we have both pieces, all of the information the question is giving us, let's set up our thermal equilibrium problem. So we know that the heat lost from one part of the system is equal to the heat gain from the other part. So we can write the heat from the copper is equal to negative the heat from the water. Right? The heat lost in one is the heat gained in the other. So we could set that up. So since we have all of the pieces of information that we have for water, let's find the Q for water. So the Q for water is going to be equal to the mass, which is 95.7 grams, times the specific heat capacity, 4.18 joules per gram per degree Celsius, times the temperature change, which is 24.2 degrees Celsius minus 22.7 degrees Celsius. If you punch all of this into your calculator, you get a number like 600.039 joules. Joules because the grams cancel out and the degrees Celsius cancel out. Now, if you were keeping track of the significant figures, you'll realize that we'll need two significant figures here. I'm just going to highlight that for now to remember later. But I'm going to keep the full number because we don't really need to round until our final answer. So now we have the Q from water. Let's figure out the Q from copper, the heat from copper. So the heat from copper will be equal to the mass of copper, which we don't know, times the specific heat capacity of copper, which we said was 0.385 joules per gram per degree Celsius, times the temperature change. The final temperature is 24.2 degrees Celsius, minus the initial temperature was 65.4 0.4 degrees Celsius. So degrees Celsius will cancel out in that case. So if we solve all of this, you do the subtraction and the multiplication, you get a value here of minus 15.862 to 3 sig figs. We'll come back to that later, times the mass, times the unknown mass. So that's our Q for copper. So now we know our Q for copper in terms of M, because M is still unknown. We know the Q for water. So let's put these two things together. So our Q for copper that we found was minus 15.862. The units here should be joules per grams. So joules over grams times the mass M that we don't know. And that should be equal to negative the Q from water. Right, so the Q from water is 600.039, so this should be equal to negative 600.039 joules. Okay, so let's solve for mass by dividing both sides by minus 15.862, so we'll have minus 600.039 joules divided by minus 15.862 joules per gram. So the joules cancel out and our answers will be in grams, which makes sense because we're solving for mass. The minus signs will cancel out and you plug this into your calculator and you will get 38 grams. Remember, this 600 is the 2 sig figs and the minus 600 is the 2 sig figs and the minus 15 is the 3 sig figs. We're dividing, so we keep the 2 sig figs. So we only round here in the end when we're looking for our answer. And our answer to number 6 is 38 grams. So the mass of copper in this example was 38 grams. If you haven't done number 7 yet, please pause the video now, try number 7, and then I'm going to go over it right now. All right, so let's look at number 7. In the case of number 7, we have a piece of rebar, and we have water. So those are two substances in thermal contact. So let's see all of the pieces of information that we do have. So for the rebar, we have a mass of 360.0 grams. Let's see. The final temperature of the water, so the final temperature is 42.7 degrees Celsius. Calculate the initial, so that's the final temperature of both the water and the rebar. The initial temperature of the piece of rebar is what we need to find, so that's the unknown. And the other piece of information that we need is the specific heat capacity of the rebar, which they tell us is the same. We use that for iron, which is 0.449 joules per gram per degree Celsius. Okay, let's look at all the information that we have for water. The mass of water we don't have, but we have the volume. So the mass of water we know we can get from the volume. It's 425 milliliters, that's the volume, and times the density of water, which is 0.997 grams per mil, right? Which, if you don't know, you should look up. Some people just use 1 gram per mil, and that's okay too. And so this will give us 423.73 grams, but the 3 sig figs, we'll remember that later. So that's the mass. They didn't give us the mass, they give us the mils, but we could find the mass easily. All right, the initial temperature of the water was 24.0 degrees Celsius, so the initial temperature was 24.0 degrees Celsius. The final temperature of water was 42.7 degrees Celsius. And the specific heat capacity of water, which they don't give us in the question, but we've used so often, we know what it is. Or if you don't know what it is, we go up to the table, all the way up here, that has specific heat capacities of various materials. Water is 4.18, sorry. So let's, yep, here we are. Let's add that. It's 4.18 joules per gram per degree Celsius. Okay, now that we have that, we know that the Q from the rebar should be negative the Q from the water. right? The rebar is our system, the water is our environment, so the heat lost from one should be the heat gained from the other. Looking at this, we are missing an information for the rebar, but we have all of the pieces of information we need to calculate Q for the water. So let's calculate Q for water. The Q for water should be the mass of water, which is 423.725 grams, times the specific heat capacity, 14.18 joules per gram per degree Celsius, meaning that the grams will cancel out, times the temperature change, which was final was 42.7 degrees Celsius, minus the initial, which is 24.0 degrees Celsius. You plug all of this into a calculator and you should get 33121.12 joules, right? Because the degree Celsius also cancels out. And this will be to 3 sig figs, which we'll use later. All right, so that's the Q for water. Let's see if we can find the Q for the rebar. All right, the mass of the rebar, they give us 360.0 grams. The specific heat capacity we looked up, 4.449 joules per gram per degree Celsius, so grams cancel out. And the temperature difference would be the final temperature, 42.7 degrees Celsius, minus the initial temperature, which we don't know, so let's just keep it as Ti. So if we multiply all of these numbers together, we'll get we'll get 6902.028 joules, right? And this is the 3 sig figs, minus 360 by 0.449 times negative Ti. So that gives us minus 161.64 Ti, which is also the 3 sig figs. Okay, so we have the Q for rebar, we have the Q for the water. Let's set them equal to the negative of the other. So the Q for the rebar is 6902.028 joules minus 161.64. That really is joules over degrees Celsius times Ti. And then that should be equal to negative the Q from water, which is, so that'll be negative 33121.12 joules. All right, to solve for Ti then, what we need to do, so Ti is equal to, we take this minus 33121.12 joules, we subtract this on both sides, so it will disappear on the left hand side, so that'll give us minus 6902.028 joules, and then we divide by negative 161.64 to cancel out that. So minus 161.64 joules over degrees Celsius. So the joules will all cancel out and our answer will be in degrees Celsius. So make sure you understand this step here in the algebra. I just subtract out this number from both sides and then I divide by this number on both sides to solve for Ti. And so if we do all of this, if I punch in the number, let's say on top here first, I get something like minus 40023.148, but this answer should be to 3 significant figures, right? And then on the bottom here, we divide that by negative 161.64, and the entire answer comes out to be 247 to 3 sig figs degrees Celsius. So that's the initial temperature of the rebar. Again, once you get to this point here, it's all just algebra. So lots and lots of algebra, but it's just algebra, which if you're not comfortable with, you'll need lots of practice. Hopefully you did get that one correct. If you haven't tried number 8 yet, pause the video and then I'll go over it with you after you're done. Okay, so let's look at number 8. We have a piece of copper and we have water. So those are 2 substances. Let's see what information we get from each. So for copper, they give us the mass, 248 grams, right? That's right there. The final temperature of the water was 39.9 degrees Celsius. So they give us the final temperature of the water, 39.9 degrees Celsius. They didn't give us the CS for copper, but here's the thing. it's copper. They tell us what the material is, which means we can scroll all the way up here and find the specific heat capacity for copper, 0.385. So even though the question didn't give us that information, we knew where to find it. So it's going to be 0.385 joules per gram per degree Celsius. And so the question is, calculate the initial temperature of the piece of copper. So the initial temperature of the copper is the unknown that we need to find. Okay, let's look at water now and what they give us. So for water, the mass is, well, we don't know what the mass is, but they give us 390 mils of water, so we can convert that to mass using the density, 0.997 grams per mil, which will give us a mass of, let's see, 388.83 grams, according to my calculator, to 2 sig figs, which we'll use later. The initial temperature of the water was 22.6 degrees Celsius. The final temperature is the same all the time, which would be 39.9 degrees Celsius. And the CS for water, again, they didn't give us, but we know where to find that. It's 4.18 joules per gram per degree Celsius. Okay, now that we have all of that set up, we do know that the Q from the copper will be negative the Q from the water. And we have all of the information that we need to calculate the Q from water, so let's do that. So the Q from water, the heat from water, will be the mass, which is 388.83 grams, times the specific heat capacity, which we've used so many times already, times the temperature change, 39.9 degrees Celsius minus 22.6 degrees Celsius. Those will cancel out, grams will cancel out, and so the Q from water will be 28117.85 joules to 2 significant figure. If you don't know where I got the 2 significant figures from, it's actually from this part of the calculation. 39.9 minus 22.6 gives us a number that's the 2 sig figs. And then when we multiply it by the other numbers, we can only end up with 2 sig figs. Okay, that's the heat from water. What about the heat from copper? We don't have all of the information, but we can calculate something. So we have the mass, we have the final temperature, we have the specific heat capacity, but not the initial temperature. So let's set it up. We have 248 grams as the mass, 0.385 joules per gram per degree Celsius as the specific heat capacity, and 39.9 degrees Celsius as the final temperature, but we don't know the initial temperature. We need to solve for that. Okay, so if you multiply 248 by 0.385 by 39.9, you get 3809.652 units of joules, and that's to 3 sig figs. If you multiply 248 by 0.385 by negative t, you get minus 95.48 times ti, negative 95.48 times ti, and that's the 3 sig figs. Okay, now that we have that, let's set the two heats equal to the negative of each other. So the heat from copper, 3809.652 joules minus 95.48, that's joules over degree Celsius, times Ti. And that's all equal to negative the heat from the water. So negative this value. So that will be negative 28117.85 joules. Okay, so we need to solve for Ti. We're going to do the same tricks that we used last time. Minus 28117.85 joules. We subtract this number on both sides. So minus 3809.652 joules. And then we divide by negative 95.48 on both sides to solve for Ti. So minus 95.48 joules per degree Celsius. The joules will cancel out. We're left with degrees Celsius as our answer. Let's figure out what it would be. If I do the top part, I get something like minus 31927.5. This was I'm trying to remember sig figs here. This was the 2 sig figs, this was the 3 sig figs. This number then comes out to be just 2 sig figs. That would be the least significant digit. So you divide that by minus 95.48 and we'll get to 2 significant figures, an answer of 330 degrees Celsius. Let me know if any of my calculations are incorrect. I maybe punched numbers incorrectly in my calculator. That could happen. Otherwise, otherwise we can go over any of these results over again. But let's go over the last one that we have for today, or rather for this video, which is number 9. If you haven't worked it yet, please do so now. Okay, let's look at number 9. Number 9 says we have a piece of metal. This time they don't tell us what the piece of metal is, but I think we'll find out in the end. A piece of metal and water. Water is almost always our second system, our second substance. They're both in thermal contact and reach thermal equilibrium. Okay, let's see all the pieces of information that we do have. All right, so the piece of metal, so let's call it metal. We have the mass of 59.7 grams. We have initial temperature. So it says that the piece of metal had been submerged in boiling water. If it was in boiling water, what's the initial temperature? Well, that's 100 degrees Celsius. We're going to use 100 exactly. And the final temperature, when everything has reached thermal equilibrium, is 28.5 degrees Celsius. And what else do we need? We need the specific heat capacity of the metal, but because we don't know what this metal is, that's unknown. In fact, the question is asking us to determine the specific heat capacity of the metal and also use that to identify the metal. So that's our question. All right, so let's see what else we have. We have the information from the water. So the water, H2O, the mass is, we don't know the mass, but they give us the volume as 60.0 mils. So let's find the mass using the density by multiplying it by the density, and that will give us a mass of 59.82 grams to 3 sig figs. The initial temperature of the water, 22.0 degrees Celsius. The final temperature, 28.5 degrees Celsius. And the specific heat capacity of water we know as 4.18 joules per gram per degree Celsius. Okay, this is all good. That means that when we set up our system, our heat from the metal will be negative the heat from the water. And since we have all of the information from the water, we can calculate the heat from the water. So let's do that. The heat from the water is equal to the mass, 59.82 grams, times 4.18 joules per gram per degree Celsius, times the temperature change, 28.5 degrees Celsius minus 22.0 degrees Celsius. We plug all of this into our calculator, we get 1625.3 joules to 2 significant figures. All right, let's calculate the heat from the metal. The mass of the metal was 59.7 grams, right? The specific heat capacity of the metal is unknown, so we'll call it the CS of the metal. And then the temperature change was 28.5 degrees Celsius as the final temperature, minus 100 degrees Celsius is the initial temperature. So if you subtract this and then multiply it by 59.7, multiply it by the CS of the metal, we get something like negative 4268.55 grams times degree Celsius. So it's grams times degree Celsius times the specific heat capacity of the metal, which we don't know. Okay, so now that we have some type of expression for the heat from the metal, some type of expression for the heat from the water, let's set them equal to minus each other. So the Q from the metal is minus 4268.55 grams times degree Celsius times the CS of the metal. and that's equal to negative the heat from the water. The heat from the water is 1625.3 joules, so it'll be negative 1625.3 joules. If we would like to solve for the CS of the metal, then we just need to divide both sides by negative 4268.55. So we have 1 minus 1625.3 joules divided by minus this value right here, 4268.55 grams times degrees Celsius. So look at that. The units are going to be joules divided by grams times degrees Celsius, which is the units for the specific heat capacity. So we know we're on the right track if we're keeping track of units. And you punch these numbers into your calculator, you'll get a number like 0.38. Remember, up here, this was just 2 sig figs. So this was 2 sig figs. So our answer will only have 2 sig figs. So that's the specific heat capacity of the metal, which is this first part of the question. The second part of the question is identify the metal. So we have 0.38 joules per gram per degree Celsius. Let's go up to our table and see what we have. We have all of these different materials. The one that's closest, it looks like, is copper at 0.385 joules per gram per degree Celsius. So I think we can confidently conclude that this material is copper. All right, so I hope we got all of these questions correct. If you didn't, you can always send me a message, come to my office hours, and we can go over any of them in detail. Otherwise, I will see you in the next video. Bye.